Quantum entanglement. It's one of those ideas in physics that just sounds completely wild. But here's the thing. It's not just a concept. It's something scientists can actually build right now in a lab. So in this explainer, we're going to look at the recipe, the actual physical steps they use to create this bizarre and incredibly powerful phenomenon. Okay, let's dive right in.
I mean, this is really the core question, isn't it? How can you have two particles, maybe billions of miles apart, that are so deeply connected that if you measure one, you instantly affect the other? It sounds like it's straight out of science fiction. It feels like it breaks every rule we have about space and time. But this spooky action at a distance, as Einstein famously called it, is a very, very real part of our universe.
So let's get practical. Enough with the mind-bending theory for a second. We're going to pull back the curtain and look at the actual physical mechanism that physicists use to entangle photons, the fundamental particles of light.
All right, before we start building, we need to know exactly what it is we're trying to build. So first up, let's nail down what entanglement really is and why it's so important, not just for crazy new tech, but in nature itself.
At its heart, quantum entanglement, or Ryoshi Motsure, as you see here from our source, is all about connection. You know the children's story Swimmy, where all the little fish swim together to look like one giant fish? Well, entangled particles are kind of like that. They basically stop being individual things and start acting as a single unified system. Their properties are linked. If you find out one is spinning up, you know instantly the other is spinning down, even if it's on the other side of the galaxy. It's wild.
And believe it or not, this isn't just some weird trick for physicists in a lab. Nature has been using entanglement for millions of years. Take migratory birds. They have these proteins in their eyes that create entangled electrons. The Earth's magnetic field messes with these electrons in a certain way, and that allows the birds to literally see the magnetic fields to navigate the entire globe. And now, we're trying to copy nature's homework to build powerful quantum computers, using entanglement to protect their incredibly fragile calculations from making errors.
Okay, so if we're going to build our own entanglement machine, we need our ingredients and our tools. So, let's meet the star of our show, the photon, and the key piece of hardware that lets us play around with all its quantum weirdness.
Our main building block is the photon, or Cauchy, a single particle of light. But in the quantum world, it's more than just light. It's a little package of information. We use it as a quantum bit, or qubit. And unlike a normal computer bit that's stuck being either a 0 or a 1, a qubit can be, well, something much, much stranger. And that strangeness has a name: superposition. You've probably heard of a double-slit experiment, right? If you fire one electron at a wall with two slits, it doesn't just go through one slit or the other. It acts like it goes through both at the exact same time, creating a ripple pattern with itself. That's superposition. A single particle exists as a wave of possibility, being in many states at once, right up until the moment we look at it.
So how in the world do we create this bizarre state of both at once on purpose? Well, it turns out the main tool is actually surprisingly simple. It's an optical component you might find in a camera or a telescope. It's called a beam splitter.
Here's how this special mirror at the Hantokyo works its magic. You take one single photon and you aim it at the splitter. Now, because it's semi-transparent, there's a 50-50 chance it'll pass straight through and a 50-50 chance it'll bounce off. But this is quantum mechanics. It doesn't just pick one. The photon's wave of possibilities splits, and it does both. It enters a superposition where it is simultaneously traveling down the path where it went through and the path where it reflected. Just like that, with a special mirror, we've created superposition.
Okay, we've got our photons. We've got our beam splitter that creates superposition. We have all the parts. Now let's put them together and build the actual engine that generates quantum entanglement.
The absolute heart of this whole operation is a quantum logic gate called the controlled NOT gate, or CNOT for short. Think of it as a tiny decision maker for qubits. This little device is the key. It's the specific mechanism that can take two totally separate photons and link their fates together forever.
So the CNOT gate needs two photons to work. One is the control photon, and the other is the target photon. Its job is pretty simple, really. It's a conditional operation. It just looks at the control photon, and based on what it sees, it decides whether or not to do something to the target photon.
The logic itself is super straightforward. If the control photon is in the 0 state, the CNOT gate does absolutely nothing to the target photon. It just lets it pass by. But if the control photon is in the 1 state, the gate reaches out and flips the target state from a 0 to a 1 or a 1 to a 0. It's just a simple if-then command.
Aha!
But here's where the magic happens. We just learned how to use a beam splitter to put a photon into a superposition. So, what happens if our control photon isn't just a 0 times or a 1, but is in a superposition of being both 0 and 1 at the exact same time when it enters the C0 gate? And this slide right here shows the physical circuit where it all goes down. When our control photon, which is both 0 and 1 at the same time, goes into this gate, the gate has to follow both rules at once. The 0 part of the photon says, hey, do nothing, but the 1 part is yelling, flip the target! And the result? The target photon is forced into a superposition of being both flipped and not flipped. And right there, in that moment, its fate becomes permanently linked to the control photon. That's it. That's the moment entanglement is born. They're not two separate photons anymore. They're one system with one shared destiny.
So there you have it. That's the recipe. We know how to create entanglement. But, knowing the recipe and actually baking a perfect cake are two very, very different things. So let's look at the huge challenges ahead and the incredible future that's waiting for us, if we can get this right.
Yeah, the biggest problem by far is that these quantum states are just unbelievably fragile. The tiniest interaction with the outside world, a stray particle of heat, a random little vibration, can just shatter the whole superposition and break the entanglement. It's a process called quantum decoherence. It's why the very first entanglement experiments could only keep the link going for a few centimeters. We've gotten a lot better, for sure, but fighting off this environmental noise is still the #1 engineering challenge in all of quantum computing.
This quote from the source material really just puts everything into perspective, doesn't it? Nature has already figured all this out. Photosynthesis, how birds navigate, these are the answers. They are perfect, optimized quantum systems. But we're like students who've been given the answer key to a test, but none of the formulas or equations. We can see the right answer, but we're still trying to work backwards to figure out the how-to.
And that really brings us to the final big thought. Building these little entangling circuits, this is our first real step in learning nature's how-to guide. By really understanding and mastering these fundamental processes, we're not just building faster computers. We're actually learning to speak the language of the universe itself. And the real question is, once we become fluent in that language, what on earth will we create?